Good afternoon. So this is going to be a bonus video in which I do one more example. So what you have presented to you in the video for section 4.4 should be more than enough for you to be successful in the homework and the exam. But just in case you want to see another example, here we go. So let's go through what's going on here. So let's talk about e to the negative x squared. And this function is the normal distribution function. If you've seen statistics, you'll know exactly what I'm talking about. And if you haven't, then that's okay. But this is the bell curve. So we know that it's going to look a little something like this. So let's talk about domain. So the domain of f is all real numbers. And f of x is going to be greater than 0 for all x. Because, so... And we know that f of negative x is the same of f of x because we have that x squared. So we know that this is an even function, so it better be symmetric around the x-axis. I'm going to erase this just so there's no spoilers. So whatever happens on the left better happen on the right. Now let's talk about extreme values and inflection points. And these follow from the derivatives of f. So using the chain rule, we have So our first derivative is negative 2x times e to the power of negative x squared, while our second derivative is 2e to the negative x squared times 2x squared minus 1. Critical points will satisfy f prime of x equals 0. And that's only going to happen in one place, which is 0, because we need 0. We can, e to the power of something will never be 0. So we need negative 2 times something to equal 0, and that answer is going to be 0. So we have a critical point at x equals 0. That means we've got a place where our derivative equals 0. Next, let's talk about inflection points, and that's going to be where our second derivative equals 0. And again, because nothing we plug into this portion will get 0, we need to solve this for 0. Which means we've got possible inflection points at x equals plus or minus 1 over root 2. So our next step is to do concave up, concave down, and increasing and decreasing. I'm going to draw my number line. And then we can plug in between negative infinity and 0, we can plug in any value we want, maybe negative 1, and get out whether we're increasing or decreasing. And in fact, we're going to be increasing. So f prime of x is greater than 0. So from negative infinity to 0, we're increasing. And then we do the same thing, plug in positive 1, and we get that f prime of x is less than 0, means it's decreasing. So now we just have to test concavity at 4 places. Here, 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 and here. And when we test concavity, we're going to get f double prime is greater than 0, f double prime is less than 0, f double prime is less than 0, and f double prime is greater than 0. And we know from that slide that I showed in the previous lecture that when f prime is greater than 0 and f double prime is greater than 0, we've got something that is concave up and increasing. When f prime is when f prime is greater than 0 and f double prime is less than 0, we've got something that is concave down and increasing. And that's just from plugging in the combinations of f prime and f double prime. So now all we have left to do is use the second derivative test to find out what's going on right here. And because we have a change in concavity, we know we've got inflection points here and here. And as it turns out, this is actually a local maximum. And we can do that by taking in 0 and plugging it into our second derivative. And when we do that, when we plug in 0, we get e to the 0, which is 1. So we get negative 1 times 1 times 2. That's a negative number. It's negative 2. We've got a number less than 0, means we've got a local maximum. So let's go ahead and graph this function. We know we've got inflection points, a local maximum. So we go from being increasing in concave up to increasing in concave down to decreasing in concave down to decreasing in concave up. And that looks exactly like the bell curve that we were describing to begin with. So we can graph any function we like when we know information about its second derivative and its first derivative.